In this video, we're going to finish section 2.7. The topic is graphing techniques. Mostly we've been talking about transformations, but there's one more thing we want to discuss. It's the idea of even functions and odd functions. And so the definition of an even function is a function that's symmetric about the y-axis. And an example of this would be the function y equals x squared. And you can see that the left side of the graph is a mirror image of the right side of the graph, and vice versa. Algebraically, we can say that f of negative x is equal to f of x for all x in the domain of the function. And so what we're saying there is, for example, if this point right here is at 2, 4, then the mirror image is right over here at negative 2, 4. And so in this particular example, the value of x would be 2. F of negative 2 is equal to f of 2. They're both equal to 4. And so if that's true for all of the values of x, then you have a graph like this that's a function like this that's even. There's another basic function that's also even. Can you think what it is? It's the absolute value function. Okay, so that's an even function, and then an odd function is symmetric about the origin. And what that means is rotational symmetry of 180 degrees. And so the example would be y equals x cubed. And so you can see that if you rotate the graph of 180 degrees around the origin, then that doesn't change the graph at all. The piece up here in the first quadrant would go exactly where this piece is down in the third quadrant, and vice versa. And so algebraically, we can say that f of negative x is equal to negative f of x. And you could think of that, you might understand that better if we consider the point at 2, 8 and the corresponding point at negative 2, negative 8. So this algebraically, this rule says if you change the sign on the x value, say from 2 to negative 2, then all you're going to do is change the sign on the corresponding output, in this case from 8 to negative 8. Again, this is for all x in the domain of the function. And once again, there are a couple other examples of basic functions that meet this criteria. Can you think what they are? The cube root function also has odd symmetry. And in fact, y equals x is also an odd function. So three examples of odd functions there. Okay, so let's go on and let's try this example. It says determine whether each of the following functions is even, odd, or neither. And the way we want to do this is algebraically. Probably that should be in the directions. I'm not sure if it's in the directions in the homework or not, but that's the expectation. So our strategy then is to check f of negative x and compare it with f of x and see what we get. So what we're going to do is we're going to say, okay, f of negative x is equal to, and we're going to replace x with negative x in the formula. We'll have 8 times negative x to the 4th power minus 3 times negative x squared. And then we're going to simplify. And so negative 1 gets raised to the 4th power and becomes a positive 1. And x to the 4th is just x to the 4th. So this is 8x to the 4th power. And negative x to the 2nd power is a positive x to the 2nd. So we're going to wind up with negative 3x squared. And of course, that's exactly the same as f of x. So we're going to substitute negative x for x. We're going to simplify the expression, and then we're going to compare it to the function we were given in the first place. And when we see that the simplified form is exactly the same as f of x, we can conclude f of negative x is equal to f of x, and so this function is even. Let's do it again. This time f of negative x is equal to 6 times negative x to the 3rd power minus 9 times negative x. And so negative 1 to the 3rd is negative 1 times 6 is negative 6 x cubed minus 9 times negative x is plus 9x. We've simplified here. Now this is not the same as f of x, but if you look at it, the sign on each term is exactly the opposite of the sign on each term in the original f of x. And so what we can do is we can factor the negative out here. We can say this is a minus, and then we'd have 6x cubed minus 9x. And then, of course, that is the same as f of x. So f of negative x is the same as negative f of x. And so this function is odd. One more. F of negative x this time is 3 times negative x squared plus 5 times negative x, which is the negative 1 squared makes a positive 1 times 3 is 3x squared minus 5x. Now, when we look at this, this is similar to f of x, but it's different, right? The signs are not exactly the same, and they're not exactly the opposite either, right? The sign on the first term is the same, but the sign on the second term is different. And so in this case, f of negative x is not equal to f of x, and it's also not equal to negative f of x. In this case, the function is not even or odd. We'll just write neither. So The algebra is the important idea here in this problem. Being able to check f of negative x is what we're trying to learn to do. But it's also nice to connect that up with the graph. And so what I've done here is I've got the graphs of each of these three functions to show you. So let's go back to the first one, 8x to the fourth minus 3x squared. We said it was even. And sure enough, when we look at the graph here, this graph on the left, we see that it certainly appears to be symmetric over the y-axis. Similarly, the next one, the 6x cubed minus 9x, when we look at the graph, that function certainly appears to be odd, certainly appears to have that rotational symmetry of 180 degrees, symmetric about the origin. And then the last one is neither even nor odd. There is some symmetry, but it's not over the y-axis and it's not around the origin, right? This is a parabola. It's symmetric about the axis of symmetry, but that's a whole different discussion for a whole different day. So this function is neither even nor odd. There's one more thing I want to look at here. We've seen even and odd symmetry algebraically, and we've seen it in a graph. Let me show you a shortcut here. When we're just working with these polynomial functions, like we have in this example, then we can just look at the powers on the variable. In part A, we have the fourth power and the second power. Those are both even numbers, and so even symmetry. In part B, we have the third power and the first power, and so those are both odd powers, and so we have odd symmetry. In part C, we have the second power and we have the first power. That's an even and an odd, and so they conflict with each other, if you will, and so we have neither type of symmetry. So this is a nice shortcut just when we're dealing with polynomial functions. That's all for section 2.7.